Today I'll be going through the questions and answers series for complex numbers in polar. So the first question, which is complex numbers given by P and Q, these values, and R and S are given by these values, where R contains an unknown number K, which is the real part of R, and R is inside S, where S is given by the modulus and argument, which essentially gives the value of S in polar form, P and Q in the numerator and denominator. Now whenever we have powers of complex numbers with the fractions, we need to change them into the polar form so that it is much easier to work with. So we have P is equal to 1 minus I, and what is it in polar form? That's the modulus will be equal to root 2, right? 1 squared plus 1 squared holding root EI. Now, referring to an argon diagram, we have 1 minus I located here, right? The length 1 and the height 1. That's negative pi over 4. So the argument is negative pi over 4. And for Q, it's equal to 1 plus root 3i. Right, the modulus would be 1 squared plus root 3 squared. That's 1 plus 3, 4, and root that will be 2. EI. Now, 1 plus root 3i is all the way up here, right, with a height of root 3. So its argument would be tangent inverse of root 3, which is pi over 3. So we have 2ei pi over 3. And finally, S is equal to, S is mainly given by these values in the question, and that's EI negative 2 pi over 3. Now all we need to do is to substitute into the main equation, which is S is equal to P squared R over Q to the power of 3. So let's just slowly substitute without making any careless mistakes. Is equal to P squared, and that's root 2e to the power of negative I pi over 4 squared. R is equal to K plus I over Q to the power of 3. Now Q is this thing to the power of 3. So we have half e negative I 2 pi over 3 is equal to 2e negative I pi over 2 over 8ei pi times K plus I. Now we want to make K plus I the subject, so we need to convert all this chunk into the left hand side somehow. So we have, well, let's just simplify the fraction first. It's equal to 1 over 4 e. Now negative pi over 2 minus pi, that's negative 3 pi over 2 K plus I. And now let's divide both sides by this value, and we get 2e negative, I times negative 2 pi over 3 plus 3 pi over 2. Alright, is equal to K plus I. Now this value over here is equal to, let's convert it over 6 with negative 4 pi plus 9 pi, and that's 5 pi over 6, right? So we have the left hand side is equal to 2ei 5 pi over 6 is equal to K plus I. Now in order to equate the real and imaginary components, we need to convert back from polar into Cartesian form, and that's 2 times cosine 5 pi over 6 plus I sine 5 pi over 6, which is equal to 2 times negative root 3 over 2 plus I times half, which is equal to negative root 3 over 2 plus I, and that's equal to K plus I. Now the way to find out if your answer is correct is to equate the imaginary part. Now equating the real parts, we have K is equal to negative root 3. Right, now on to the second question. We have, given that u is equal to this value in Cartesian form and w is equal to this value, find the modulus and argument of u conjugate over w to the power of 3. Now, since it's in fraction form again, we need to convert them into polar coordinates. But this is really easy because we have, just remember that e to the power of I theta is equal to cosine theta plus I sine theta, right? And e to the power of negative I theta is equal to cosine theta minus I sine theta, which is the conjugate of e to the power of I theta. Right? These two formulas bearing in mind, we can convert them in one single step, which is u is equal to 2 times e to the power of I pi over 6, right? Because this is the theta in this case, and for the other side, it will be the theta value for e to the power of negative I theta. So we have w is equal to 4e negative I pi over 3 And that makes things really easy because we have u conjugate over w to the power of 3 is equal to 2e negative I pi over 6, rather, right, the conjugate of ei theta over 4e negative I pi over 3 whole thing to the power of 3, and that's equal to 2e negative I pi over 6 over 64, right, 4 to the power of 3, e negative I pi, and that's equal to 1 over 32 times e to the power of I times negative pi over 6 plus pi, and we get 1 over 32 times e to the power of I, 5 pi, no negative, is positive, 5 pi over 6. So the modulus would be 1 over 32, and the argument would be 5 pi over 6, solved. Moving on to the next question, we have shown that the complex number, which is this one over here, can be expressed as this complex number over here. So let's solve the first part first. We have z is equal to 1 plus, now the skill in this question is converting from polar form into the Cartesian form and then converting it back into polar form. So we have z is equal to 1 plus that is 1 plus cosine of negative pi over 3 plus I sine of negative pi over 3, and that's equal to 1 plus, now cosine pi over 3 is equal to cosine negative pi over 3, right? So we have that's equal to half minus I sine of pi over 3, and that's equal to root 3 over 2, and we have 3 minus root 3i whole thing over 2. Now we need to express this in terms of the polar form, so we need to find its modulus. So we have modulus z is equal to, what do we have? We have 3 over 2 whole thing squared plus root 3 over 2 whole thing squared, whole thing rooted, and we have, now we can take half out first, 3 squared plus 3, right, and we have half times the square root of 3 squared plus 3, that's 12, right, and taking out the 4, we have the answer to be equal to root 3. Now moving on, we have the argument of z is equal to the argument of, okay, now we need to use an Argand diagram here, right, makes things really easy. So we have 3 over 2 is over here, and we have negative root 3 over 2 is over here. So we have the ratio of the rise over the run is equal to root 3 over 3, right? So we have, now the ratio of this over this is equal to root 3 over 3, and thus the tangent of that is equal, tangent inverse of that is equal to pi over 6, and because it's negative pi over 6. So we have argument of z is equal to negative pi over 6. And now with these two values, we can piece together the modulus and the argument of the polar expression of z, and that's root 3 times e to the power of I and its argument, which is negative pi over 6. Now the complex number zw has modulus 5 and argument 3 pi over 4. So find the complex number w in polar form. So we have zw is equal to its modulus 5 and argument e to the power of I 3 pi over 4. Right? So we know what z is. So all we need to do is divide the right hand side by z. So we have w is equal to 5ei 3 pi over 4 over z, and z is equal to root 3 e negative I pi over 6. Right? All we need to do is just to do the math. So that's 5 root 3 over 3, rationalizing the denominator, and we have e to the power of I times 3 pi over 4 plus pi over 6, right? Because they're dividing by that. And that's equal to 5 root 3 over 3 times e to the power of I. Now what's 3 pi over 4 plus pi over 6? Now over 24 we have 18 pi plus 4 pi, right? So that's 22 pi over 24, and that's 11 pi over 12. Done. Right, moving on to the next question, we have find the imaginary part of this chunk over here. Now, we have e to the power of 7i theta minus e to the power of 5i theta Right, how on earth do you actually make this easy for you? Now, when we want to know the imaginary part of this, we need to change this into Cartesian form, right? And it's much easier to work with conjugates because we have e to the power of I theta plus its own conjugate, or plus its own conjugate. We have 2 cosine theta because the imaginary part cancels out, and we have e to the power of I theta minus its own conjugate. We have, what do we have? We have 2i sine theta, right? And this is converting polar coordinates into its Cartesian form. So all we need to do is to find pairs of conjugates, right? To minus off each other or plus each other off, and we can get the imaginary part in a way easier form. So we have this is equal to, now we want to find conjugates in the denominator, so we have e to the power of 6i theta, right? E to the power of I theta minus e to the power of negative I theta. Now this looks really familiar, right? And in the denominator we have e to the power of negative I theta times e to the power of negative 2i theta minus e to the power of 2i theta. Right, so taking away the multiplier outside, we have, what do we have? We have e to the power of 7i theta, and in the denominator we have, right, e to the power of I theta minus its own conjugate, and we have 2i sine theta, and in the denominator we have e to the power of a negative 2i theta, and that's cosine of let's do the math outside here. So we have cosine of negative 2 theta plus I sine of negative 2 theta minus cosine of 2 theta minus I sine of what do we have? 2 theta, right? And since cosine cancels away, we have I sine negative 2 theta minus I sine 2 theta. And take note, because sine of negative theta is equal to negative sine theta, we have it's negative I sine 2 theta minus negative I sine 2 theta. So we get negative 2i sine of 2 theta. Right, so we have the denominator denoted as negative 2i sine of 2 theta. So we get e to the power of 7i theta times, now 2i cancels out, and we have sine theta over negative sine 2 theta. Now we need to change this into something easier to work with, so we have negative 2 sine theta cosine theta, the double angle formula, and you'll know that sine theta and sine theta cancels out, so we have this is equal to e to the power of 7i theta over, negative e to the power of 7i theta over 2 cosine theta. Now, this is something that's way easier to work with than this chunk over here, right? So the imaginary part of this, now we need to find the imaginary part of negative e to the power of 7i theta over 2 cosine theta. And that's also equal to the imaginary part of negative cosine of 7 theta minus the I times sine of 7 theta over 2 cosine theta, right? And just by looking at this, we know that the imaginary part is located over here. Right, so that's negative sine of 7 theta over 2 cosine theta. There you have it. Now let's move on to the last question. Two complex numbers w and z given by modulus and argument as follows. Express wz in Cartesian form and hence show that sine of 7 pi over 12 is equal to this value. So first we need to express wz in Cartesian form, which is the first part over here. So we have wz is equal to, we have root 3 e negative I 3 pi over 4 times, that's w, so we have z, that's e negative I 2 pi over 3, right, the modulus and the argument. And that gives you root 6 e of, we have I negative 3 pi over 4 minus 2 pi over 3. And this gives us root 6 e to the power of negative I 17 pi over 12. Right, and multiplied by e to the power of I 2 pi. Right, this value is equal to 1. So whenever you see that the value on top here exceeds pi or negative pi, We can multiply it by e to the power of I times 2 pi or negative 2 pi, which is equal to 1. And that allows us to simplify it to 7 pi over 12. Right, because if you look at an Argand diagram, right, negative 17 over 12 is over here. Right, and this is the same as the argument 7 pi over 12. So we have Wz is equal to root 6 ei 7 pi over 12, which is also equal to root 6 of cosine 7 pi over 12 plus I sine 7 pi over 12. Now this is one way to express Wz, but the other way is to actually multiply Wz and obtain a value in terms of Cartesian form, which is in the form of x plus iy without trigonometric identity. So we have Wz is also equal to root 3 of cosine of negative 3 pi over 4 plus I sine of negative 3 pi over 4 whole thing times z, which is times, so write next line because there's no space, root 2 times cosine of negative 2 pi over 3 plus I sine of negative 2 pi over 3, and that gives you, right, so let's take out the root 3 and root 2, that gives you root 6. And for w we have, this is 3 pi over 4 is in the third quadrant, so we have negative root 2 over 2 minus I root 2 over 2, right? Negative for the third quadrant of sine. And negative 2 pi over 3 is also in the third quadrant, so we have negative half minus root 3 I times root 3 over 2. Right, so we take out all the halves, which is root 6 over half times half, that's quarter. Take out all the negatives, so it's all positive, so we have root 2 plus I root 2 times 1 plus I root 3. And this gives you root 6 over 4 times root 2 minus root 6, right? All the real values. Now all the imaginary values, we have I and this root 2. And what else do we have? We have also root 6. Right, so we got these two terms are the same. So equating the real and the imaginary components. So equating the imaginary components, because we want to find out sine, right? We want to find out sine of 7 pi over 12. So left hand side is equal to root 6, right? Not forgetting the magnitude of sine. We have root 6 times sine of 7 pi over 12. And the right hand side is equal to, what do we have? We have root 6 over 4 times root 2 plus 6, right? And equating left hand side to right hand side, we have, right, so you equate these two together, we get root 6 sine 7 pi over 12 is equal to root 6 over 4 of whole thing multiplied by root 2 plus root 6, and cancelling off the root 6's, we have obtained the identity and we have it proven.